Hello everybody, in this video we're going to be looking at Unit 3 using the distance formula in the coordinate plane. Our learning objective is I can use the distance formula to analyze and reason about the properties of figures plotted in the coordinate plane. Alright, so let's take a look at our problem here. What we're going to do in this problem is we're going to use the distance formula to determine whether the provided quadrilateral is or isn't a kite. Right, so I have a figure here in the coordinate plane, and we're going to determine whether or not this figure, this quadrilateral, is a kite. So if you're wondering what a kite is in terms of geometry, we have a definition here. A kite is a quadrilateral whose four sides can be grouped into two pairs of equal length sides that are adjacent to each other. So that definition is a little bit wordy, so it's maybe better to just look at the quadrilateral and kind of see what it's talking about. So there are four sides, and it says there's grouped into two pairs of equal length sides that are adjacent to each other. So the word adjacent means next to. So the two sides that are the same length need to be next to each other. So I'm noticing that this side length here and this side length here are about the same length. And this side length here and this side length here are about the same length. So I'm going to put congruency ticks on here and here. And I'm going to say that and that. These two are the same length and these two are the same length. So that is my claim to show that this is a kite. But what we have to do to prove that this quadrilateral is a kite, we must show two things. So we have to show that these are congruent to each other and that these are congruent to each other to actually prove that this shape is in fact a kite. All right, so let's put this more in geometric notation now. So we need to show that the side length WX is congruent to the side length WZ. So to prove that this quadrilateral is a kite, we need to show that WX is congruent to WZ, meaning that they are the same length. And likewise, we need to show that this side length is congruent to this side length. So we need to show that XY, side length, XY, there we go, is congruent to side, we can call it ZY. ZY. So we need to show that these two things are true in order to prove that this quadrilateral is in fact a kite. So I'm going to do number one first here. I need to show that WX is congruent to WZ. And to do that, we need to figure out how long each side is. And in this case, this is actually pretty easy to figure out the side length because it's on the x-axis and this one's on the y-axis. So what we can do is just kind of count our way over from W to X. This one goes from -3 to 2. And notice that the 3 and the y-axis are the same. So it doesn't change in the y. So this thing is just 1, 2, 3, 4, 5 units long. So our WX is equal to 5. And our WZ, that is 1, 2, 3, 4, 5 units as well. So by this, I have shown that WX is congruent to WZ. So that's good. The second one is going to be a little bit harder to show because it doesn't just go along one of the axes. It actually go at a little bit of an angle. So this is where we're going to have to use our distance formula. So we're going to have to show that XY is congruent to ZY. All right. So So let's figure out how long xy is first. All right, let's deal with xy. This length right here. Now it's not along one of these axes, so we can't just count the boxes as we go along, right? But what we've kind of learned in this module here is that the distance formula in the coordinate plane is essentially just the Pythagorean theorem. So what we can do is turn this into the hypotenuse of a right triangle by doing this here. We go from x, we go along our x-axis here, we go along our y-axis here. So we still have xy is now our hypotenuse of this little right triangle that we created over here. All right. Now we can find the side lengths of this right triangle in order to help us find the hypotenuse. All right. I'm going to put kind of a third point there. So I have this right triangle here. I'm trying to find the hypotenuse. All right. So this right triangle has side length 1, 2. So this has 2, and this has 1, 2, 3, 4, 5, 6, 7. All right, so this side length is 2, this side length is 7, and this is a right triangle. So I'll draw the little right angle in there. So what we're going to do is use the Pythagorean theorem in order to find this distance right here. All right. So just to kind of confirm, our Pythagorean theorem is a squared plus b squared equals c squared. And in this case, we have our a and our b, and we're trying to figure out what c is. In this case, xy is our hypotenuse. So I'm going to rewrite this as 2 squared plus 7 squared. That's going to be equal to, I'll just call it xy squared, because that is our distance, xy. 2 squared is 4. 7 squared is 49. That is going to be equal to our xy squared. 4 plus 49 makes 53. That is still our x squared. We take the square root of both sides. So xy is going to be equal to the square root of 53. All right, now we know how long xy is equal to. Let's figure out how long zy is equal to. Very similar setup. This is not along one of the axes, so we can't just count these boxes as they go along, right? This is longer than that. So what we do is we make a right triangle, come off from point Z, come down and over. So we have our right triangle here. This comes down 1, 2. So that has side length of 2. And this comes over 1, 2, 3, 4, 5, 6, 7. So you may have noticed that this right triangle right here has a 2 and a 7, and this one has a 2 and a 7. So I can already tell that we're on the right track, that this is going to have the same side length as this one here. But just like anything else, we got to show that it's true again. So I'm going to use my Pythagorean theorem. I'm going to know that 2 squared plus 7 squared is going to be equal to my zy squared. Again, 2 squared is 4 plus 49 equals zy squared. This is equal to 53 equals zy squared. Take the square root. Just ran a little bit out of room. We're going to figure out that zy is equal to the square root of 53. That's how long it is. Don't have a calculator on me, but it's a little bit more than 7. So about 7.2 or something like that. You could do that on a calculator, square root of 53. But the most important part is that we showed that xy and zy have the same length. So xy and zy have the same length, so that's why they are congruent to each other. And we also showed that wx and wz have the same length. So now we can actually say that yes, this thing is a kite. If for some reason these lengths were different from each other, these two lengths were not the same length, then we could not say that this is a kite. So remember, your definitions are important, and then you have to prove that your definition is in fact true. All right, there's a problem on the back side to show. So go ahead and do that on your own. Thank you.